Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. Today, we're diving into a huge pain point for engineers, how to turn those complex designs into reality without, completely blowing your budget or your prototype.
Look, we've all been there, right? You're deep into a project, you've poured time and money into building that physical prototype, and then it fails. Sometimes it fails in a big, expensive way. So now you're right back at square one, your timeline is a mess, and your budget is just hemorrhaging money. It can feel like you're just stabbing in the dark. But what if there was a way to test, to iterate, and to basically perfect your design before you even touch a single piece of metal?
Yeah, that whole traditional cycle of build, test, break, it's a total nightmare. I mean, it is wildly expensive, just eating up materials and lab time. It's so slow. Every single new version can take weeks, even months. And for some systems, think aerospace or anything with high pressure, physical testing can be legitimately dangerous. And here's the kicker. Even when a prototype does work, you often get very little insight into why it's working. And if you want to change one little thing, well, you're starting that whole expensive process all over again.
So that brings us to the real heart of the issue, doesn't it? How do you really put something through its paces when it's just an idea, just a drawing on a screen? How can you ask all those critical what-if questions about a system that hasn't even been built? Well, the answer is the engineering superpower we're going to talk about today.
That answer, that superpower for engineers, is mathematical modeling. And hey, before your eyes glaze over thinking this is just going to be a bunch of abstract theory, just stick with me. We are talking about a seriously practical tool that can completely change the way you approach design.
So what is it, really? At its core, a mathematical model is just a way to describe how a system behaves using the language of math. It's a set of equations that really captures the physics of what's going on, the relationship between force and acceleration, or voltage and current. It's basically a way to create a virtual, predictive copy of your design.
A fantastic way to think about this is to think of a map. Imagine you had a map that was a perfect one-to-one scale replica of the entire world. It would literally be the size of the planet. It would be completely and utterly useless. But a simple subway map? It gets rid of all the extra noise, the street names, the buildings, and it only shows you exactly what you need to know, the stations, the lines, and how they connect. A subway map is useful because it's simple, and that is exactly how we need to start thinking about our models.
And that leads us to a really important idea in modeling. It's often kind of counterintuitive, but it's a mindset shift that really separates the good engineers from the great ones. It's all about the pursuit of the good enough model.
This right here is the whole ballgame. The goal is not to build the most complicated, ultra-precise model you possibly can. No way. The goal is to build the simplest model that can answer your specific question and help you make a smart design decision. More complexity isn't better. In fact, a lot of the time, it's your worst enemy.
And this slide really nails that trade-off. On the one hand, if you go chasing that so-called perfect model, you wind up with something that's way too complex to actually solve by hand. It takes forever to build and run, and all that extra detail can actually hide the very insights you're looking for. But on the other hand, a simple, good enough model, well, that's something you can actually solve and analyze. You can iterate on it super fast, and it reveals the fundamental behavior of your system. It gets you 90% of the way there in like 10% of the time.
Okay, so the theory is cool, but how do we actually build one of these things? Let's take a really common example and just break it down step by step. We're going to model a basic car suspension. Now, to do this, we don't need to model every single nut, bolt, and washer. Instead, we use what are called ideal elements. Think of these as the basic Lego bricks that represent how a system stores or gets rid of energy.
For a mechanical system like this, we can boil pretty much everything down to three basic elements. First, you've got things that store potential energy, and the classic example is a spring. Second, you have elements that store kinetic energy because of their motion, like the mass of the car body. And third, you have elements that get rid of energy. They dissipate it, like a shock absorber that turns motion into heat. Our whole complex suspension system can be represented with just these three building blocks.
And this all comes together in a really clear four-step process. First, you define your system. What are the parts? What are you trying to do? For our car, that's the wheel, the chassis, and we want good ride comfort. Second, you build that lumped element model, swapping out the real parts for our ideal mass, spring, and damper. Third, you apply the fundamental laws of physics, like Newton's laws, to describe how these things all interact. And finally, you combine all of that to get the set of differential equations that is the mathematical model of your suspension.
So now you've got this beautiful model on paper, but how do you actually turn those equations into a better car on the road? That's the key, right? We have to move from the page to the computer. Your model gives you that theoretical backbone, but digital tools, that's where you get to play. That's where you experiment, optimize, and really push the limits of the design, all without having to build a single thing.
And simulation is how we run experiments on our model. Look, we can't always solve these complex equations by hand, but a computer has no problem with it. Simulation lets us run hundreds of virtual tests in a single afternoon. What if we make the spring stiffer? What if the damper is weaker? What happens when the car drives over a huge pothole? Simulation gives us the answers.
But even in the digital world, there's no such thing as a free lunch. There's always a fundamental trade-off in simulation. If you want a super accurate result, your computer needs to solve the equations in teeny tiny increments of time. We call that a small time step. But that takes a ton of processing power and time. On the flip side, if you use a larger time step, the simulation runs way faster, but you lose some accuracy. A big part of the art is finding that sweet spot that gives you a result that is, you guessed it, good enough, without having to wait all day for your computer to finish.
All right, to wrap this up, let's do a quick rapid-fire round and tackle a few of the most common what-if questions that always pop up when you start doing this in the real world.
Because real-world systems are messy, they aren't perfectly predictable. So what do you do when you have things like random wind gusts hitting an airplane wing or electrical noise messing with a circuit? How on earth do you model that?
This is what we call a stochastic system, one that has randomness baked into it. And models are actually perfect for handling this. Instead of telling your model, the wind is exactly 20 miles per hour, you tell it something much more realistic, like, well, the wind averages 20, but it could gust up to 30 or drop to 10, and it follows this probability curve. You run the simulation thousands of times with those random inputs and you don't get one single answer. You get a whole range of likely outcomes, which is so much more useful for designing a system that's truly robust.
Okay, this is a big one. So far, we've mostly been talking about linear systems, where if you double the input, you double the output. But a lot of real-world parts, like a spring that gets way stiffer right at the end of its travel, they aren't linear at all. So what do you do then?
And the answer, believe it or not, brings us right back to our main idea. You simplify. You probably can't model that entire nonlinear behavior easily, but you can create a very accurate linear model that works perfectly within a specific range you care about. Picture a big curve. If you zoom way in on just one tiny section of it, it looks almost like a straight line. That's exactly what linearization is. We create a simple, good enough model for the exact operating point we're interested in, and that lets us solve really complex problems using simple tools.
So, at the end of the day, modeling gives you this incredible power to see the future, to test things that are impossible to test in real life, and to just design smarter. The question you always have to be asking yourself isn't, is my model perfect? It's, is my model useful? Knowing just how simple you can make it while still getting the answer you need, well, that's not just science, my friends, that is the art of great engineering. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.